Hello guys, I am Ali Jawad and welcome to my YouTube channel. In this video, we will start with chapter number 23 of Physics Syllabus 5054 for Cambridge students. This content is in the continuation of chapter number 22, Electromagnetism. So I am providing link over here so that you can have a review of chapter number 22 before proceeding with chapter number 23. So in chapter number 22, we have learned that how electric current can be used to produce magnetism and how electric current and magnetism can interact to produce force. In this chapter, we will going to reverse it. Means in this chapter, we will learn how magnetism can be used to produce current and how magnetism and force act together to produce current. So let us start with the basics. The fundamental law in electromagnetic induction is proposed by a scientist, Michael Faraday. When he observed in his laboratory that whenever the magnetic flux changes through a coil, a deflection on the galvanometer was observed. Means whenever the magnetic lines of forces changes through this coil, a voltage is observed on this galvanometer. Note that it is not important for the magnetic field to be there. What important is that the magnetic field may get continuously changed. So, however, there are certain factors which he has determined that can affect the voltage produced or EMF induced. These factors are the number of coils, the strength of the magnet, and the speed of the magnet or coil relative to one another. So let us do it experimentally. Over here, I have a simulation which shows the apparatus used by the Faraday in his experiment. As you can see, we have a magnet over here and a coil attached to a voltmeter. Note that if I slowly move the coil in this magnet or magnet into the coil, no deflection is observed. However, when we start to change the magnetic field in a fast manner or the magnetic field changes rapidly, the deflection is observed on the galvanometer. So there are multiple factors which can increase deflection. It includes the number of coils. So for example, from here in the simulation, I will try to change the number of loops and then we will going to see the effect on the deflection. So I have increased up to by 3 coils and now I am moving the coil. So now you can observe that deflection is more. We can replace it with a bulb, reducing the number of loops as it was before. Now the bulb is giving light. Note that when the magnetic field is there, the voltage is not being produced. When the magnetic field gets changes, then only the EMF is induced. EMF means electromotive force. You can for the time being consider it as voltage. So when we have lesser number of loops, although EMF is being produced, now let us try to increase the number of loops. And when we are moving the magnet through the coil, now the light bulb is giving more light. So it suggests that the EMF produced or the voltage induced has increased with the number of loops. Note that we can do vice versa. means we can move the coil and can hold the magnet stationary. So that is why it says the relative movement. The relative movement with respect to one another. Note that if I may move this magnet with a low velocity, the EMF will be there, but the power or the extent of EMF induced will be low. Or you can say there will be lesser amount of voltage. However, if we may increase the velocity of movement, so the EMF induced is increased. So that is why we have seen that the induced EMF is directly proportional to the number of coils, because as the number of coils increases, the induced EMF increases. Same goes for the magnetic field and relative velocity of the magnet or the coil, because one of them might be in the moving position and one will be stationary. So these factors can affect the induced EMF. Now there is another important law which has a fundamental position in electromagnetic induction, that is known as Lenz's law. Lenz's law says about induced current. The induced current means the current produced because of the movement of coil or because of the movement of magnet. It says that induced current is always in the opposite direction of the magnetic field. And what does it mean? Let us see it diagrammatically. For example, we know that the magnetic field from north to south can be drawn as the arrows shown. So when we will move the coil rightward, means the magnetic field is moving rightward in this case. So the induced current which is being produced is towards left, as you can see the direction of arrows shown in the wires. Now, it can be a vice versa case. For example, if we may move the magnet into the coil, so the direction of the movement will be opposite to the direction of current, and the current is produced in the opposite direction. As you can notice, the arrows giving the direction of current. This is a kind of opposite behavior, and every normal being, either it is living or non-living, has this kind of resistance. We all does not accept the changes too easily. You can relate it with the inertia of an object, for example, because the object does not translate suddenly or does not come suddenly into the state of rest from motion, or from the state of motion into the state of rest. We also do not accept sudden changes in our daily life. For example, sudden change of the weather cause our health to get disturbed. So the coil also shows the opposite behavior, because it does not accept the sudden change in magnetic field, and it tries to oppose it with the current flowing in the opposite direction. Lenz's law particularly is very important in determining the direction of opposite behavior, or Lenz's law can also give the direction of induced current. Note that it does not give the direction of voltage, because voltage is the amount of energy carried by the electron, and we do not need to associate any direction with the voltage. But current has particular direction. So these are the fundamentals of electromagnetic induction. I hope that you have enjoyed the lesson. Don't forget to subscribe our channel to watch the latest videos on the same content. Thank you for watching.